Hello and greetings to everyone. We are going to continue from where we ended last time. Today what we are going to treat is application of nature of roots. The application of nature of roots of the quadratic equation. Application of nature of roots. When we treated nature of roots, we saw that the quadratic equation can either have two really distinct roots, repeated roots, or complex roots. Let's take this down. When sketching the graph of a quadratic function, y equal to ax squared plus bx plus c, for x belonging to the set of real numbers, always take note of the sign. When we talk of the sign, that means whether it is positive or negative or positive. The sign of the coefficient of x squared, which is e. You always take note of that. Let's look at the various cases. We go by the margin. We take I if e is greater than 0. That means e is positive. Remember, e cannot be equal to 0. If e is positive, the parabola. Remember, when we sketch quadratic functions, the curves we obtain, they are called parabola. The parabola is a valley parabola. You know how a valley looks like. It has the form of a bowl. It's a valley parabola. That is, you have something of this shape like this. That's a valley parabola. We take now 2i. If e is less than 0, that means e is negative. The parabola is a mountain parabola. You know how a mountain looks like. It's a mountain parabola. I underline mountain parabola with a red pen. And that is, you have something of this shape, goes up and comes down. When we have a valley parabola, we are going to say the function, the quadratic function, has a minimum point. When we have a mountain parabola, we are going to say the quadratic function has a maximum point. We take this down. Recall that for a quadratic equation, ax squared plus bx plus c equal to 0, when you go by the margin, take the first hyphen in the discriminant b squared minus 4ac is less than 0. That means when it is negative, we know the quadratic equation has no real roots. Has no real roots. We take note of this. We move now to the second hyphen. When the discriminant b squared minus 4ac is equal to 0, we treated this, we saw this under the discriminant. In this case, we are going to say the quadratic equation has repeated roots. We move now to the third hyphen. When the discriminant b squared minus 4ac is greater than 0, in this case, we are going to say the quadratic equation has two real distinct means they are different, two real distinct roots. If we take the third hyphen, I'll write this one with a red pen because most of them will be making good use of this. When the discriminant is equal to b squared minus 4ac is greater than or equal to 0, in this case we are going to say the quadratic equation has real roots. Remember, when the roots are repeated, the roots we have, they are real numbers. When the roots are two real distinct roots, they are real numbers. So if the discriminant is greater than or equal to 0, we see the quadratic equation has real roots. We take this small paragraph by sketching the graph of y equal to ax squared plus bx plus c, for x belonging to the set of real numbers, we can easily identify the type of roots the quadratic equation ax squared plus bx plus c equals 0 has. We get the quadratic equation by replacing y here with 0. So by sketching the graph of this function, it is very possible for us to know the type of roots this quadratic equation has. Now it depends on whether the curve of this function curves the x-axis at two distinct points, or it touches the x-axis at one point, or the curve does not touch the x-axis at all. Now let's look at the various cases. In the sketches below, a is greater than 0. That means we'll be dealing with valley parabolas. Take the first one, let's draw the first case. This is our x-axis, and this is our y-axis. It's always very important to label the axis. In this case, the curve of y equal to ax squared plus bx plus c touches the x-axis at one point. So in this case, it touches the x-axis at this point. We are going to say the quadratic equation ax squared plus bx plus c equal to 0, has repeated roots. It has repeated roots or equal roots. Now to 2i, in the next case. For this case, the curve cuts the x-axis at two distinct points, and it's two different points. This is our x-axis, the origin, our y-axis. In this case, we have the curve as such. Because the x-axis at 2 points here and here. In this case, we are going to say the quadratic equation ax squared plus bx plus c equal to 0, has two real distinct roots. Has two real distinct simply means they are different roots. Now we go to the next case, 3i, where the curve does not touch the x-axis. No, x-axis, y-axis. In this case, our curve is suspended as such. In this case, we are going to say the quadratic equation ax squared plus bx plus c equal to 0, has no real roots. Or has complex roots. We are going to see how to get the complex roots when we treat complex numbers. Now let's take this down. The three sketches above, of the various cases of the curve of y equal to ax squared plus bx plus c for greater than 0, shows the possible cases. Let's look at the possible cases. For the first one, I is the first sketch. The curve touches the x-axis at which is the x-axis at 1 point. That is y equal to 0, the quadratic equation has repeated roots, as we have seen above. We go to 2i, the second curve. The curve cuts the x-axis at 2 distinct, that means they are different, 2 distinct points. That is for y equal to 0, the quadratic equation has 2 real distinct roots. We go to 3i, the curve does not touch the x-axis. That is for y equal to 0, the quadratic equation has no real roots or has complex roots. That's what it simply means for the 3 cases we have above. Now let's take examples. You see how to handle questions on these problems on these examples. The first question goes, question 1, find the range of function f of x equal to x squared plus 6x minus 1 for the domain. Means the function has domain x belonging to the set of real numbers. When we talk of the range is simply the set of images of the function f of x. We take down solution. For us to find the range of this function f of x, we are going to make good use of the method of completing the squares. We have f of x is equal to x squared plus 6x minus 1. This will equal to x squared plus 6x. We are going to add a half the equation of x, all that squared. The equation of x is simply 6. A half of 6 is 3. We are going to add 3 squared. Bring down negative 1. Then we subtract 3 squared. Remember, 3 squared minus 3 squared, and the cancel off will go back to this. The reason why we are simply doing this is for us to obtain a perfect square, and this is a perfect square, of which the factorization is simply x plus what we have in bracket c plus 3, all this squared. When you do the expansion of this, you go back to what we have up here, this expression. We treated this under finding the maximum value of a quadratic function, the maximum or minimum value, minus -1 minus, we know 3 squared gives us 9. And this will simply be equal to x plus 3 all the squared. -1 minus 9 gives us -10. We have been told that the domain of the function is a set of real numbers. For every x we take from the set of real numbers, we know x plus 3 squared will always be greater than or equal to 0. And the case where this will be equal to 0 is when x is equal to -3. -3 plus 3 gives 0. 0 squared remains 0. But for all the other cases, the results will be greater than 0. The next step, we are going to add -10 at the left hand side, and at the right hand side of this, our inequality, -10 greater than or equal to 0 minus 10. Remember, when we add a constant at the left hand side and at the right hand side of an inequality, the inequality sign does not change. This will give us x plus 3 squared minus 10 is greater than or equal to 0 minus 10 remains -10. We know this is our function f of x, the quadratic function. It therefore means for every x we take from the set of real numbers, comma, of function f of x is greater than or equal to -10. Now we can write down the range of this function. The range of our function f of x, the range will simply be equal to y, which is equal to f of x, comma, where f of x is greater than or equal to -10 for x belonging to the set of real numbers. So this will be the range of our function f of x, and y here is also a real number. We move now to the next example, example 2, which says find the range of values of beta for which the quadratic expression x squared plus 4 beta x plus beta is always positive. It's always positive for all real values. All real values of x. We take solution. We know for the quadratic expression x squared plus 4 beta x plus beta to always be positive. That means the graph of this our quadratic function x squared plus 4 beta x plus beta does not touch the x-axis. It is always positive when the curve of this does not touch the x-axis. So in this case, it simply means if we let our y to be equal to 0, that means 4, that is x squared plus 4 beta x plus beta equal to 0, then the discriminant of this quadratic equation will be less than 0. That's what it means. We know the discriminant is given by b squared minus 4ac. Now if we compare this our quadratic equation, comparing x squared plus 4 beta x plus beta equal to 0 with ax squared plus bx plus c equal to 0, we have a to be 1, which is the equation of x squared, b to be 4 beta, this is x, so b will be 4 beta, and our c will simply be equal to beta. It therefore means our discriminant will be equal to 4 beta all is squared minus 4 times e, which is 1, times c, which is beta. And this will simply be equal to 4 squared gives us 16 beta squared minus 4 times 1 remains 4 times beta gives us 4 beta. So this will simply be equal to 4 beta times 4 beta minus 1. Now for x squared plus 4 beta x plus beta to be always positive, for all real values of x, then the discriminant must be less than 0. It is positive for all real values of x. That means if you draw the curve of y equal to x squared plus 4 beta x plus beta, the curve does not touch the x-axis. It simply means if we take this our discriminant 4 beta times 4 beta minus 1, it is less than 0. That's what it means. And this is a quadratic inequality which we can solve. But the first thing, we need to find the critical values. When we talk of the critical values, we are simply referring to those values that when we insert them for beta, we replace beta with those values in this our inequality, we are going to obtain a result which is not true, something which is contradictory. For us to get the critical values, we are simply going to equate 4 beta times 4 beta minus 1 to 0. At this level, we are going to see either 4 beta is equal to 0 or 4 beta minus 1 is equal to 0. For us to get beta here, we are going to divide both sides by 4. And this will give us our beta to be equal to 0. Or 4 beta will be equal to, we are going to transfer -1 to the right hand side, which becomes positive. We divide both sides by 4. In this case, our beta will simply be equal to 1/4. Beta equal to 0 or beta equal to 1/4 are the critical values of this our quadratic inequality. Simply means if you replace beta here with 0, 0 times this will give you 0. You are going to obtain 0 less than 0, which is not true, which is a contradiction. So these are the critical values. Now the next thing, we need to get the required range of values. for beta such that this inequality will be true. So if we consider our quadratic function to be y equal to 4 beta times 4 beta minus 1, what we have at the left hand side here, we know if you expand this will give us 16 beta squared minus 4 beta. So if you consider this to be our quadratic function, you see that in this case our a is 16, the coefficient of beta squared. A is equal to 16, which is greater than 0. And when it is greater than 0, it simply means the graph of this our quadratic function y equal to 16 beta squared minus 4 beta is a valley parabola. And it has roots beta equal to 0, beta equal to 1/4. So these are the points where the curve of this quadratic function meets the x-axis, which is the beta axis in this case. Because in this case, this is our function y. Y is a function of beta. So now for us to get this, we need to draw our beta axis as such. This is our beta axis. Then we know we have a valley parabola since a is greater than 0, 16. At this point, if you compare the roots, you know 0 is less than 1/4. So here we have the first root, which is 0, and here we have the second root, which is 1/4. We are looking for the required range of values for which 4 beta times 4 beta minus 1 is less than 0. Less than 0, we know if we are to draw our y-axis, less than 0 simply means below the x-axis. We are going to shed the portion of the graph which is below the x-axis. This portion here. It therefore means 0. Here at 0, since they are the critical values, we have rings here. Draw the rings. Since it is strictly less than, the rings will be open. But if we had greater than or less than or equal to, then the rings will be shaded. In this case, we can give the required range of values for beta. It therefore means 0 should be less than beta. Beta should be less than 1/4. So if you take a value for beta which is between 0 and 1/4, you insert it here for all the values of x. This our quadratic expression will always be positive. It's something you can check, you can verify. Now let's conclude. Therefore, 0 less than beta less than 1/4 is the required range of values. Range of values for beta. There is still another way we can get this. Question 3, which says find the range of values. It says find the range, or range is there's an s in bracket of values. K can take for k x squared minus 4x plus 5 minus k equal to 0. We want to have two real distinct roots. For k not equal to 0, that means k must not be equal to 0. We take down solution. The first thing, we are going to start by comparing the given quadratic equation, comparing kx squared minus 4x plus 5 minus k equal to 0 with the ax squared plus bx plus c equal to 0. To compare, we have our a to be, a will be k, b will be negative 4, and our c will be equal to 5 minus k. We know that for real distinct roots, real distinct, that means they are different roots to exist. First, I have two real distinct roots. Then the discriminant b squared minus 4ac must be greater than 0. We know the discriminant is simply equal to, we are going to insert the values of a, b, c here. This will give us negative 4 squared minus 4 times a, which is k, times c, which is 5 minus k. And this will be equal to negative 4 squared gives us 16. Negative 4 times k gives us negative 4k. Negative 4k times 5 gives us negative 20k. And negative 4k times negative k gives us plus 4k squared, which is equal to 4k squared minus 20k plus 16. This is what we are going to have. But we know the discriminant is greater than 0, so if you take discriminant greater than 0, then 4k squared minus 20k plus 16 has to be greater than 0. Then you will see that 4 is common. If we divide all through by 4, this will give us k squared minus 5k plus 4 is greater than 0 divided by 4 remains 0. The left hand side can be factorized. This is a quadratic expression which can be factorized. We are going to make use of negative 4 and negative 1. Then k squared plus, I know negative 5 here can be replaced with negative 4 minus 1 times k plus 4 is greater than 0. Then k squared plus negative 4 times k gives us negative 4k. Negative 1 times k gives us negative k plus 4 will be greater than 0. Then k squared minus 4k, we know positive negative negative will stay, minus k plus 4 is greater than 0. Then looking at these two terms, we have k is common, we factor out k, times k minus 4. Looking at these other two terms, negative 1 is common, times k minus 4 is greater than 0. Then k minus 4 is common, times k minus 1, negative 1 is here, is greater than 0, which is a quadratic inequality. For us to solve this quadratic inequality, we are going to start first by finding the critical values. For us to get the critical values, we are going to equate k minus 4 times k minus 1 equal to 0. These are the critical values. We are going to equate k minus 4 times k minus 1 to 0. This will give us either k minus 4 is equal to 0 or k minus 1 is equal to 0. Here k will be 4, right here k will be 1, or k equal to 4 or k equal to 1 are the critical values. Looking at the critical values, we know 1 is less than 4. So we are going to construct a table. Let's construct our table. For the first column, we have k. For the second column, we are going to test values of k which are less than the smallest critical value, which is 1. We're going to take k less than 1. For the second column, we are going to test values between 1 and 4 for k. 1 is less than k less than 4. For the next column, we are going to test values of k which are greater than 4. The k is greater than 4. Then for the rules, so the first rule we have remember for the inequality we have k minus 4 times k minus 1 greater than 0. So for the first rule we are going to test, we have k minus 4. For the second rule we have k minus 1. And lastly we have k minus 4 times k minus 1. On this our sign table, we are only interested in the signs. We are going to take a value of k which is less than 1. We insert here, write down just the sign of the results. That's what we are going to do. So if we take, for example, 0, 0 is less than 1, we take k to be 0, which is less than 1. If we take 0 minus 4, the answer is negative 4. The sign will be negative. I'll put a negative sign here. Still using 0, 0 minus 1 gives us negative 1. The sign will be negative. We know down here we have k minus 4 times k minus 1. So we take negative times negative. The resulting sign will be positive. We move now to the next column. Here we are going to test values for k that lie between 1 and 4. If we take, for example, 3, 3 minus 4 gives us negative 1. The sign will be negative. Put negative here. If we take 3 minus 1, the sign will be positive. Put positive here. Negative times positive, the resulting sign will be negative. Next, we have to check values of k greater than 4. If we take, for example, 5, 5 is greater than 4. 5 minus 4 gives us positive 1, so this will be positive. Still using 5, 5 minus 1 gives us 4, which is positive. If we take the product positive, positive, remains positive. At this level, you will see that the required range of values, the required ranges of values will be k less than 1 or k greater than 4. For this to be greater than 0, we are going to conclude, therefore, the required ranges of values for k. We have k less than 1 or k greater than 4, which mathematically we are going to write this as we want to give it as a set. We are going to give it as such k such that k is less than 1 union k is greater than 4. So this will be the set, the required set of values, such that if you insert them in that our quadratic equation, the quadratic equation will have two real distinct roots. Moving on to the next question, we take question 4, which says that find the required range or ranges of values k can take for kx squared minus 2 kx minus 3k minus 12 equal to 0, to have real roots for k not equal to 0. Remember, for this our quadratic equation to have real roots for k not being equal to 0, then the discriminant of this our quadratic equation should be greater than or equal to 0. That's what it means. A takedown solution we compare the quadratic equation with the general form kx squared minus 2kx minus 3k minus 12 equal to 0 with ax squared plus bx plus c equal to 0. If we compare, our a will simply be equal to, this is x squared, a will be k, b will be negative 2k, and lastly c will be equal to, this is the constant term, negative 3k minus 12. We know that for real roots, we have the discriminant e squared minus 4ac to be greater than or equal to 0. That's what it means. If you look for the discriminant, it will simply be, we are going to insert the values of b, a, c. This will give us negative 2k all this squared minus 4 times a, which is k, times c, which is negative 3k minus 12. And this will simply be equal to, if we take negative 2k all this squared, it gives us 4k squared. We know negative 4 times k gives us negative 4k. Negative 4k times negative 3k, negative becomes positive. 4 times 3 gives us 12. K times k gives us k squared. Next, we take negative 4k times negative 12. Negative becomes positive. 4 times 12 gives us 48. we attach key, and this will simply be the same as 12 k squared plus, if we add 12 k squared plus 4 k squared, we can add this to their right terms plus 48k. This will simply be equal to, 12 plus 4 gives us 16k squared plus 48k. At this level, we are going to factor out the 16k. 16k is common. 16k times k gives us 16k squared plus, if we take 16k times 3, this will give us 48k. The discriminant being greater than or equal to 0 simply means 16k times k plus 3 is greater than or equal to 0. And this is a quadratic inequality which we are going to solve. So the first step, we need to start by finding the critical values. The critical values. So it's important to find the critical values. After finding the critical values, we are going to draw our sign table. We have 16k times k plus 3. We are going to equate it to 0. At this stage, we are going to say either 16k is equal to 0 or k plus 3 is equal to 0. At this stage, for us to get k, we are going to divide both sides by 16. Here, we are going to transfer 3 to the right hand side, which becomes negative 3. So this will give us k to be equal to 16, which try equals 16, k to be equal to 0, or k to be equal to negative 3. So these are the critical values. Looking at the critical values, we know negative 3 is less than 0. Now we can draw our sign table. We are going to check values of k which are less than negative 3. We check values of k which are between negative 3 and 0. And lastly, we check values of k which are greater than 0. For the first column, we have k. For the second, we check values of k which are less than negative 3. K is less than negative 3. Next, we check values of k which are between negative 3 and 0. Lastly, we check values of k which are greater than 0. For the first row, we have 16k. Remember the inequality, we have 16k times k plus 3 is greater than or equal to 0. This is what we have. If we divide all through this inequality by 16, this will give us k times k plus 3 is greater than or equal to 0 divided by 16, which is 0. But in this case, we are going to, there's a reason why we are making use of strictly less than, strictly greater than here. I know most of you will be worried why we are not making use of less than or equal to, here and greater than or equal to. We cannot make use of them here at this present stage. Remember, these are the critical values. Now let's proceed by drawing our sign table. For the first row, I'll just insert k. Instead of 16k, I'll just put k here. And I'll take note of the sign. The next row, k plus 3. The last row we have k times k plus 3. We are just to write down the signs. If we take k less than -3, for example, if we take -10, the sign of k is simply negative. If we take -10 plus 3, it gives us -7. The sign is negative. Negative times negative, we take the product, the resulting sign will be positive. Next, we have to check the sign of values of k between -3 and 0. If we take k to be -1, the sign of k is negative. -1 plus 3 gives us 2, which is positive. If we take negative times positive, the resulting sign will be negative. Next, we have to check the sign of values of k greater than 0. If we take, for example, 4, the sign of k is positive. 4 plus 3 is 7, the sign is positive. Positive times positive gives us positive. At this stage, we can state the required range of values of k. For us to state the required range of values, we are going to make use of less than or equal to now. Since the inequality we have is k times k plus 3 greater than or equal to 0. That means it is positive or it is equal to 0. So for it to be equal to 0, we know k will be equal to -3 or k is equal to 0. So at this stage now we are going to state it by saying k is less than or equal to -3 or k is greater than or equal to 0. We conclude therefore the required ranges of values of k are, we have k less than or equal to -3. For it to be equal to 0, k will be equal to -3, or k is greater than or equal to 0. Of which we can write this as given it as a set. We have k such that k is less than or equal to -3 union k is greater than or equal to 0. So these are the range of values of k such that if you make use of them, that our given quadratic equation will have real roots. I'm going to end by taking down exercises for application. Question 1 says find the range of each of the following functions with domain x belonging to the set of real numbers. For the first one, E, we have the function f of x is equal to x squared plus 4x minus 2. Question B, we have the function f of x is equal to x squared plus 3x plus 5. C, we have the function f of x is equal to 5x minus 1 minus 2x squared. We go to question 2, which says if ax squared minus 8x plus 2 is equal to 0. Has repeated roots. Find the value of E. Question 3 says find the range of ranges, that's an S in bracket, of values of K for which question E we have a K x squared plus 4x plus 3 minus K, 3 plus K equal to 0, to have real roots. Question B, we have a K x squared plus 3x plus K minus 4 equal to 0, to have two real distinct roots. Two real distinct roots. Go to question C. Question C, we have a K x squared plus 1 is equal to 4kx minus 3k, to have real roots. These are the three questions we have. Next, we are going to correct these exercises. If in case you have any problems, make sure you leave your questions at the comment section. Please, if you like the video, share and subscribe to this YouTube channel. Thank you very much for watching.